This video will be on graphing absolute value inequalities. It's really an inequality that's a function with an x and a y in the equation. But if the inequality is greater than or less than, the line is going to be dashed. If the inequality sign is greater than or equal to or less than or equal to, the line is going to be solid. Okay, so in the green here we have some notes. You might want to take this down if you don't already have them. And then the next question you guys ask is which way do I shade? If all the ones I'm going to be doing today, y is going to be by itself, and if that's the case, if y is by itself on one side of the inequality or the other, if it's greater than or equal to, you're going to shade above. If it's less than or equal to, you're going to shade below the graph, the line. And then number two, or you can use this method. You can use a point not on the line to test, and you test that point within the inequality, and if it happens to be true, you shade towards the true point. Alright, so I'll show both ways. The first one, since I don't have much room, I'm just going to go ahead and graph this. If you're unsure how to graph the line, you're actually going to graph the line y equals the negative of the absolute value of negative 3x plus 3. Okay, and then you will shade from there. So since a is negative, it's going to be a downward V. Like I said, if you're not sure how to graph this, you can look at my previous video over graphing absolute value functions. But I do know that my vertex is going to be at 0, 3, which is right here. And again, I'm expecting this thing to go downward as I plug in y's, or as I plug in x's, I get y's. I also know that my slope is 3 to 1. So I'm going to go with that route. I'm just counting 1, 2, 3 and over 1, 2, 3 and over 1. So my slope is sitting out front, and I could also check those, just kind of review. But I could plug in 1 into this inequality. That's really, I'm going to plug it into this equation, and I get, when I plug in 1, I get negative 3, but the absolute value of negative 3 is 3. But then on the outside there's a negative, so negative 3 plus 3 makes 0. So that point's right there. So I must have done my slope correct. So either way, now since it can be equal to, this line is going to be solid. Solid line. What that really means is that the points on the line make a true statement. So the points on the line are solutions to this inequality. Now, where are my other solutions? Well, if we go by this, where it says shade below and above, this is less than, so below this graph is right there. Now, why do I shade there? Well, inside here, where it's shaded, that's where all your solutions are. All right, those are all solutions. On the outside where it's not shaded, those would not be solutions. What I mean by solutions are points that make the inequality true. So we all know that 0, 0 is sitting in the middle of this. It should be true when I test it. So let's try it. I plug in 0 for y. So I'm taking this inequality here, right beside the 3, okay, and I'm going to plug in 0. And 3 times 0 is 0, and the negative of that is still 0. So this whole thing right here just kind of cancels out, and I have 0 is less than or equal to 3. That's obviously true, all right? And that makes, so since it's true, it's a solution. All right, now if 0, 0 is a solution, then all these other ones would work, including the ones on the line would be solutions. Out here, these are non-solutions. Okay, so let's go to the next one. My vertex is going to be at negative 1, 4. I know that by just looking, I got ahead of myself there. I quickly looked at that and wanted to take the opposite of that, but I'm going to back up here. I need to make this equal to 0. That's going to be my x-coordinate of my vertex, and 4 is going to be my y-coordinate. So I got to think about this one. Actually just solve it. So 3x plus 1 equals 0. Subtract 1. Divide by 3. Okay, so if you didn't quite catch that, my previous video tells you why you have to do that. Okay, so my x-coordinate of my vertex is negative 1/3, and my y-coordinate is 4. So negative 1/3, 4 is right up here. Okay, from there, you know, I can do the slope method, all right, but my slope is still 3, sitting here in front of x. But this is over 1/3. 1/3 divided by 1 makes 3. So I needed a rise of 1. All right. The other thing, to make this simple, what you could do for sure is just plug in and evaluate at 0. When x equals 0, you get 3. Oh, gotta go that way. You get 5. All right, so when you plug in 0, 3 times 0 is 0, plus 1, so this ends up being 1. 1 plus 4 is 5. So I went the wrong way. So there we go. I'm expecting this to be upward like that. All right, when I plug in negative 1, negative 1 times 3 is negative 3, plus 1 is negative 2. Okay, so the absolute value of negative 2 is 2. 2 plus 4 is 6. So when I plug in negative 1, I get 6. So this one barely fits on the graph. It's going to be solid. So that's the only little part of this graph that I have, since it's moved up so far. But either way, all right, now if it's greater than, I'm going to shade above. So just that little portion right there is going to be greater than. Now I showed this last time. If I plug in 0, 0, I like to plug in 0, 0 because it's easy to evaluate. If I plug in 0 for y, 0 for x, and evaluate, since this is not shaded over here, this should not work. It should not be a solution. So let's evaluate this. So inside here I get 1, and 1 plus 4 is 5. So I get this statement that 0 is greater than or equal to 5. So when 0, 0 was tested, I got this false statement. All right, so this ended up being false. So all these points outside of the V are going to be false. Inside is going to be true. All right, this one should go pretty quick. My vertex is 1, 0. And again, I'm expecting this to be an upwards V. My slope is 2. I could plug in 2. Think about this. 2 minus 1 is 1, and 1 times 2 is 2. So when I plug in 2, I get 2. When I plug in 3, 3 minus 1 is 2. 2 times 2 is 4. So I have this function that's growing by 2 each time. Okay, and then this thing's symmetrical also, so it's going to head up the other way in a 2-to-1 relationship. Now, I should have a dashed line. Because the points on the line are not going to be solutions. Okay, if I plugged in any one of these points into this inequality, it would not be true. All right, so since it's greater than, I'm going to shade above. Again, if I tested 0, 0, you will end up with a false statement. Therefore, it is not a solution. Just plug it in real quick. 0 is greater than 2. 0 minus 1. Okay, so I'm testing it here. I get 0 is greater than, this is 2 times 1. 0 is obviously not greater than 2. So I've proved that that is not a solution, so the other solutions are going to be away from that. Okay. So again, my vertex is going to be 4, 0, which is over here. I have a slope of -2, and I also know that this, since A is negative, it's going to flip over. So I'm going to go 2 to 1 this way. Should be a solid line because it's equal to. So once I have it graphed, I'm just graphing y equals, just like my previous video showed. I'm just graphing that, and then since it's greater than, y is greater than the function, it's going to be above it. So we're shading this outside. Now since I shaded 0, 0, that should come out true. Plug in 0 for y, plug in 0 for x, and I get this statement that 0 is greater than or equal to -2 times that absolute value of -4 is 4. So 0 is greater than -8. So that came out true, and it should have, because 0, 0 is sitting within the shaded region. Okay, number 7. I'm not going to make the mistake twice here. I see this right here to find my x-coordinate of my vertex. I have to set that equal to 0. And then, my k, my constant term is 0. Okay, so I got to think about this. I'm going to subtract 4 from both sides, then divide by 3. So that's 1 1/3, -1.